Hi, I'm going to look at our first example of curve sketching. Really, this is nothing new. It's just bringing together a lot of the calculus you've learned thus far. So in this example, we're going to look at the function x divided by x squared plus 1. And I'm going to show you basically the process that I'm expecting to go through on a quiz. So there'll be listed out to the side many features or attributes of the graph that I would like you to find. So all you have to do is find those things, and then at the end, hopefully you can take that information and graph the function without any use of a calculator. This will be a no calculator section. So let's just start with the first derivative. So it'll ask you for the first derivative. And so a lot of times we look to rewrite the function. In this case, that's not really going to be helpful. So I'm just going to do a quotient rule. So y prime equals bottom term times the derivative of the top, which is 1, minus the top term times the derivative of the bottom over that bottom term squared. Okay, and I will do some cleanup here because we are going to use this first derivative in just a moment for something else. So not required for this part, but to understand what we're going to do later on. So if you see, if I distribute that, I get negative 2x squared. So I have a negative x squared plus 1 as my numerator, and an x squared plus 1 quantity squared as my denominator. Okay, so that's my first derivative. Second derivative. We'll use this obviously to find inflection points for discussion of concavity. So y double prime equals bottom term times the derivative of the top minus the top term times the derivative of the bottom term over that bottom term squared, which is going to turn it into a fourth power. Boy, that thing's kind of ugly. Let's see what we can do to it. I'll bring the 2 with the 2 there. That's minus 4x times x plus 1 times x squared plus 1. I have an x plus 1 term here and here and here. So I can get rid of, I can factor out and reduce one of them. So this will turn into negative 2x times x squared plus 1 minus 4x times negative x squared plus 1 over x squared plus 1 quantity cubed. And that can even be cleaned up. So what would that be? That would be negative 2x cubed. Here I get a positive 4x cubed. So that's 2x cubed, negative 2x, negative 4x, so minus 6x over x squared plus 1 quantity cubed. Okay, so it will benefit you to clean these up because you're not going to have a calculator, so you're going to have to find critical values and inflection points later on. Okay, so continuing with this function, we are going to find the y-intercept, which sometimes confuses kids for some reason. Remember, the y-intercept is when x equals 0, okay? Remember, on your y-intercept, you're not going left to right on your graph, you're just going up and down. So we're going to just put 0 in for x squared. So y equals 0 over 0 squared plus 1, so that's 0. So I have a point. Now think about it. I put x equals 0. So I know a point that's on my graph, 0, 0. Some students actually graph as they go. I generally like to just kind of get the attributes out of the way that are asked of me and then go from there. X-intercept, okay? So that's where it crosses the x-axis, so that's when y equals 0. So 0 equals x divided by x squared plus 1. Well, the good news is that, you know, really here, this can only be 0 on top because 0 divided by anything is 0, and so that's also, you know, x equals 0. So just kind of reinforcing this point. That's kind of interesting, though, if you think about the graph that we'll eventually get to. 0, 0 is on it. Might as well graph it. Let's just talk about it. 0, 0 is there. But there's no x-intercept or y-intercept, which means my graph is either going to be kind of hanging out in the third quadrant, and this, I mean, they can hang out in a quadrant, but there's not going to be any crossing other than right here. Okay, it's the only spot that there will be hopping over the y-axis or the x-axis. So that's going to be interesting to see. Things to think about as you go through the problem. So we've got the intercepts out of the way. Let's talk discontinuities, okay? Now, generally with these type of problems, what you're going to see is a discontinuity occurring when your denominator equals 0. So, you know, you may have to be able to factor here. We're looking for point discontinuities or vertical asymptotes. Really, jumps are pretty obvious. It's a piecewise function, or it's, you know, like a greatest integer function. They're really odd looking compared to the typical rational polynomial functions that you're used to seeing. So here, I'm just going to set my denominator equal to 0. And hopefully you can see that we'll get imaginary values here. So there are no discontinuities. All right. So we've gotten those out of the way. So let's talk. So there's no vertical asymptotes. There's no points. It's going to be a continuous function on its domain. And since there's no restrictions on x here, the domain is all real numbers. Okay. Sometimes that is asked for you, but usually I highlight it in the discontinuities. Next part, end behavior. Okay. End behavior is when you're finding the limit of the function, okay, as you approach infinity and negative infinity, okay? There have been AP questions in the past that'll trip kids up because kids generally only think about infinity and not negative infinity. So we're going to find the limit as we go to both ends of the function, as we both go both ways, okay? So you got to remember your functional dominance ideas. Really, where's the highest exponents? It belongs to your denominator, which means this is approaching 0 on both parts. So your end behavior, you can just leave like that, because there will be a question generally asked about horizontal asymptotes. Sometimes I'll ask about vertical asymptotes. You would just write none, okay? In this case, horizontal asymptotes, look, your end behavior is going to tell you what that is. Now, I don't want to see just 0. I want to see y equals 0. Okay? So I actually am going to go back to the function at this point. If that horizontal asymptote's y equals 0, we can kind of just dash a line across here, knowing that as we get out to the extremes, it's going to be approaching that. So that maybe helps us see it a little bit. Next part, critical values. These are lengthy, okay? I may have to go into a part 2 of this video. Critical values is when your first derivative is equal to 0, and you're going to solve there, okay? Or where the function is not differentiable, which in this case everything was good, okay? There's no weirdness occurring here. But my first derivative, I'm going to use the cleaned up version, negative x squared plus 1 over x squared plus 1 quantity squared. I mean, if you look at the denominators, there's no value in there that's going to produce a 0. So really, in most cases, I'm just going to look at that numerator and set him equal to 0. Okay? And so in that case, you get x squared equals 1. And so x equals not just 1, it's plus or minus 1. Okay? So those are my critical values. And so from there, you could be asked about possible points of inflection. Let me put that on a new page. Okay, possible inflection points. We're going to take that second derivative and set it equal to 0. And as before, the denominator is going to be totally fine. No discontinuities, no issues. And so I'm going to set the numerator equal to 0. And you know what? I'm running out of time. We'll have to continue this on another video.